Greetings, everyone. This is Lucas speaking. I'm the team leader of the Gonzaguinha 1 mission from the Asa Branca Aerospace Extension Program by the Federal University of Pernambuco, Brazil. And today we're going to present a critical design review for a 500-meter apogee rocket. I'd like to start off by saying this is actually Asa Branca's first ever attempt to make a full rocket from tip to tail with a self-made propulsion system. So our main objective in this project is rapid iteration for learning purposes. We try to make a very standard rocket following the general rules of thumb and making an effort to do hand calculations whenever possible, documenting every step of the way because, as I said, this is our first step in rocketry design, therefore we didn't want to be reliant only on softwares. We also needed to learn the equations, parameters, and thought process behind these programs to make our own decisions. Besides the rules and requirements of the LASC competition, we also try to adapt our rocket's components to our specific needs and known restrictions at every available opportunity. The material and design choices were made with all that in mind, so we can manufacture some of these parts and verify our concept design as soon as possible. With that said, we actually would classify this presentation as a preliminary design review, owing to the fact that we are fully aware what and where our rocket's flaws, and our plan is to continue working on that before we make any definitive decision about our design. But here is what defined for now. This is an overall view of our Gonzaguinha 1 rocket. It has about 1 meter in length and 85 millimeters of sternal diameter with a 3FNC configuration, 3 fins and 1 nose cone. The motor mount will be fixed in place by plywood centered rings and will also be the core where the fins will be glued in. On the end of the motor mount, we also made sure to add a screw and cap to hold our motor inside the rocket. On top of the motor section, we have the payload, a pocket cube satellite, and then the avionics and recovery bay that we'll be talking about in a moment. Here's the fun part. This is a rocket propulsion system, a fully reusable motor assembled with an aluminum 6061 case along with a 1020 carbon steel bulkhead and nozzle which are rigidly bolted into the case, both making use of O-rings to withstand the high pressures of the propellant combustion inside. Speaking of it, our propellant choice was KNSB. As far as the grain geometry, we chose a standard tubular core shape inhibited by epoxy resin in its outer surface and separated in two segments of equal length. This configuration is also known as a base grain, and we use it to maximize burning area and therefore achieve our desired thrust curve. For the nozzle geometry, we went with a set of 40-15 half angles with an exit diameter of about half the size of the motor mount, giving us a nozzle with a length which was sufficiently fine to fit the O-rings in both threads we desired.
Hello everyone, I'm Gisele and I'm going to talk about the rocket aerodynamics. This subsystem aims to minimize the drag of the rocket body and ensure stability while we reach the apogee. To achieve a good flight performance, we use the Open Rocket software to simulate flights with different configurations. And then we choose the 3FNC model that is composed of a PVC pipe tangent nose cone and 3 tapered swept fins made with plywood, the same material as the scenery rings. The fins of our rocket also have an extension base to secure them into the motor tube, using a technique called through the wall. With this choice of geometry, we intend to simplify its construction and maintain good aerodynamics for the rocket body. Through these settings in the Open Rocket software, we obtain a static margin of 1.96 calibers, Mach number of 0.30, and drag coefficient of 0.45, which are very similar to the parameters we obtained from the Barrowman equations.
As for the recovery of a rocket, to choose which system would fit us best and to analyze the flight and landing conditions, we did some research and then the CO2 powered ejection method was chosen. In order to determine the parachute sizing, we performed drag coefficient estimations and then verified our choice by calculating the reduction of descent rate, which was about 23%. Therefore, the parachute will have a 70.28 centimeters diameter canopy. The parachute will be made out of nylon, and the suspension lines as well as the shock cord are made of rigging ropes. We also added a swivel link in the connection between the shock cord and suspension lines. With the thermal expansion due to the CO2 power system, a tape thermal control was placed into the fuselage where the recovery system is located. So, this is it for now. We appreciate the opportunity to participate in the last competition. Follow us on Instagram for more updates on our Gonzaguinha 1 rocket.